Hey guys, welcome to the Quick Bits, the channel where we quickly talk about the most important bits of a computer science. And in today's video, we'll talk about the most confusing question in programming, probably in the whole history of humanity. Why zebras have such a big butts? Just kidding. The real question is stack versus heap. Which one is cooler? I'm sure every programmer heard of those terms, stack or heap. Some of us know that allocation on a stack is faster, on a heap is slower. We heard of terms like stack overflow is when you do a lot of recursions. Your stack overflows, your program crashes. But I don't think many of the programmers actually know why is that. Why stacks faster? Why heap is slower? So in today's video, let's look into details. Why is that happening and how that works. One way to remember the difference between the stack and a heap is to imagine the bunch of construction bricks and compare them to the bunch of rocks that you can find on the street, anywhere. So as you remember in the construction site, you can put the bricks one on top of the other quickly, right? You put the cement, you put the brick on top of it, and if you mess it up, you can quickly remove it, right? So it's a very quick process. Anybody can do it. Some interns probably can even do it. On the other side, the issue with rocks is you have to be really smart about putting them together, right? Because as you can see, some rocks are really big, right? And some rocks are very small. So you should be very careful when you put them together. And sometimes there's gaps, in between the rocks. In this case, in this picture, like for example, like over here, right? There's a gap. So this is very similar to what happens when the memory gets fragmented, because memory will try to put the rocks in the proper order. So for example, let's say you can just put like huge rock over here, right? Because it will fall. So what you have to do, you will have to take the small rocks out, put this big rock probably over here somewhere, right? And then put the small rocks on top of it. So that's what the operating system does for you. Actually, if you try to look at large blocks, it will try to find the space for you. And if you can find the space for you right away, you will have to move all the small blocks around, right? So that's why the memory management in the heap is way more expensive. That's why it takes much longer to allocate the heap. Step deeper here. So this is the representation of a stack in memory. It's a very high level representation. So it's a little bit more complex than this, but I think will suffice for our case. So before we talk further about the stack, let me mention this thing called the stack frames. So the stack frame is the thing that gets generated when you call a function. So when you call a function, right, there's a couple things involved, right? So first you have to pass the arguments to a function, right? Then you have to know the return address of the function, because after function gets executed, you have to come back to some point, right? So you have to store the return address, right? Also in the stack. Then there is like various registers that needs for the function. And of course the local variables that you create inside a function itself, right? So the local variables also called automatic variables. So all this stuff that I just mentioned is stored in the stack. It's easy to put in, and once the function gets executed, all these objects that get created, they get popped from the stack, right? So as the function call happens, you put more stuff. As the function exits, you pop that stuff. So it's pretty simple, right? It's just really like a stack data structure. And then of course you store all the earlier frames, right? So when the stack overflow happens, right, it's one common error in recursion. What really happens is that you keep calling functions and you keep storing more stack frames in the stack, right? You're like boom, boom, boom. That's why actually stack overflow happens, right? Because the stack usually is like on some Linux boxes is only 2 megabytes. So once you put all these variables in there in a recursive way, you blow up the stack. Okay, so what kind of variables stored in the stack, right? So every time you do like double B, integer, and right, all the POD variables, those stored in the stack. So now let's say you have a pointer, right? So let's say you did the new my object and you got the pointer. Where is that object is being stored? And that's where we get to the heap. The heap is basically has a similar layout as a stack, right, in memory. Of course, it's not totally true. This stack has like CPU manages stack a little bit differently as well. But what really happens is when you the new on my object, right? That my object is stored in some random place in a heap, right? Then let's say you create another my object, right? That my object must be stored here, right? And what happens is you're not always sure where exactly my object will be stored, right? It's not going to be stored right after the other one. It's not going to be stored in this fashion. It could be stored anywhere in the heap. And the other thing about the heap is like when I mentioned about the stack, right? When the function exits, all the variables get automatically removed from the stack. The thing with the heap, you have to, as a programmer, be aware that you allocated on a heap, and you have to clean up yourself. In some programming languages where the memory managed for you, like Java or .NET, the garbage collector will try to figure out, if there's any reference to a heap or not, and they will try to clean up for you. And it's actually doing a much better job these days than they used to do before. In languages like C or C++, yeah, you have to call free on it or delete on a heap, right? So if you understand the memory caches in CPU, right, like L1 cache, L2 cache, L3 cache, you can clearly see that there's a problem with the using of heap, right? So let's say like this segment of memory goes into your L1 hash, right? L1 cache in CPU, right? So then you have this in memory, and then let's say you want to refer to some other object in the heap, right? So then, okay, so now the CPU has to load this stuff as well, right, into the L1 cache, or like registry cache or something. So right away you can see that this is very expensive operation, right? Referring to because this heap could be like 2 gigabytes, right? Let's say, for example. I mean, it's in the best case, right? Right now machines could be 8 gigabytes, right? So jumping around the heap is very expensive, and that's why you have to pay that really huge penalty to allocate on a heap, right? So right now I'm keep bashing on a heap, right? But is it really that bad, right? Not really, because the stack actually very small. It's about like 2 megabytes on Linux, I think, configured, or I think on Windows is a similar thing. And the heap is much larger, right? So if you have a large objects, you have to go on a heap. I've seen programmers actually do a lot of stuff, allocation of arrays on, like I've seen programmers do some like creating arrays of size like 1 million, or maybe not 1 million, but like hundreds of thousands, right? And then they blow up the stack, and debugging that is very expensive. So allocating on a heap is not that bad. You just have to know the cost of doing that. So I think the rule of thumb is, something small, okay, put it on the stack. Something big, yeah, go on a heap. And OS actually does pretty good job in locality, and trying to figure out, what you're gonna access next. So it shouldn't be as bad. And there is also such things as a buffered allocator that will help you with the management of the heap memory. But in general, there is not much, hardware difference between stack and a heap. It's just the way the memory is managed on there. Okay guys, that's it for this video. I hope you enjoyed this stack versus heap video. Let me know in the comments who do you think is cooler, heap or stack. And please like and subscribe. Thank you.